Hello everybody, welcome back to the Gregorius Maths video. Today is sort of like a little prelude to my full counterexamples in analysis video, where I'm going to be going through all of the annoying corrections that you can provide to your friends who make incorrect assumptions in analysis. But today I want to talk about one family of functions which sort of ticks all the boxes pretty much. It does like everything. So I want to talk about the following family of functions. So it's f alpha. We're going to take in inputs from -1 to 1. And here's how it's defined. So x gets mapped to, it's defined piecewise, but only because it's not defined at x equals 0 otherwise. So it's the absolute value of x to the power of alpha times by sine of 1 over x when x is not equal to 0, and it's just 0 at x equals 0, right? Now, why is this family of functions so special? Well, first things first, when alpha is 0, you just get the topologist sine curve, which I won't talk about in detail today, but the topologist sine curve is an example of a function which is not continuous, but is integrable. So when alpha equals 0, you get a function which is continuous, not continuous, but integrable. Okay, that's the first thing. All right, now let's have a look at the derivatives. So when x is not equal to 0, the derivative, you just apply the product rule and the chain rule, and you get that the derivative is, let me use a different color. The derivative is at x not equal to 0, f alpha primed of x is just alpha, absolute value of x to the alpha minus 1 times by the sine of x times by sine of 1 over x, the two different types of sine. This is just the derivative of the absolute value of x. This is application of the chain rule. And then we have to minus absolute value of x to the alpha minus 2, because of course you have to times by minus 1 over x squared, and then cos of 1 over x. Okay, so this is at x not equal to 0, and we'll have a look at the problems with this in a second. But let's take a look at what the derivative is at 0. So the way that we compute this is we simply just plug in the definition. So this is for x not equal to 0, and f primed alpha of 0 is equal to the limit as h goes to 0 of f alpha of h minus f alpha of 0, which is just 0 by definition, all over h, which is just the limit as h goes to 0 of the absolute value of h to the alpha all over h times by sine of 1 over x, like so. Okay, now we can put a bound on this thing, right? So if we look at the magnitude of this guy, the magnitude of h to the alpha over h times by sine of 1 over x. Well, firstly, okay, let's put this all, okay, over h times by sine of 1 over x is less than or equal to, well, firstly, this sine of 1 over x is bounded by 1. Its magnitude is bounded above by 1. So already this is less than or equal to the magnitude of h to the alpha over h. But if we take out in one of these absolute values of h's, and we just get absolute value of h over h times by h to the alpha minus 1, well, absolute value of h over h when h is not 0 is just, again, the sine of h, which again is bounded by 1. So, is 1, the magnitude is 1 in that case. So we're bounded above here by the absolute value of h to the power of alpha minus 1, right? Now, here we see some issues, because when alpha is less than 1, then we get like 1 over h to the something. And so in that case, this thing is unbounded, and in fact it's going to cause the whole thing to explode, right? Because if you plug this in, alpha less than 1, you can see that this h on the bottom is going to explode, right? However, sorry, that's a pretty important thing I've said there. So when alpha is between 0 and 1, so at alpha equals 0, we're not continuous, but we are integrable. When alpha is bigger than 0, then we are continuous because this x, for small x, is going to dominate and the oscillations won't be so crazy. So we are continuous for alpha bigger than 0. However, when alpha is between 0 and 1, and we can include 1 actually because, oh sorry, this should say sine of 1 over h, by the way. We can include alpha equals 1 into this because then it's going to be plus minus sine 1 over h, which still has no limit, right? As h goes to 0, it's just oscillating infinitely. So when alpha is between 0 and 1, let me add this in here. We are continuous, but not differentiable. Okay, so we're continuous, but we're not differentiable. So again, if your friend now says to you, well, okay, you can maybe not be continuous, but still be integral, fine, I'll give you that. But you definitely can't be continuous and not differentiable. You can again show him this function and just say, well, just plug in alpha between 0 and 1, mate, and get back to me after that. You know what I mean? So anyway, all right, that's that. Now, we had that expression for f prime of x when x was not equal to 0. So now we've established that the derivative exists everywhere when alpha is bigger than 1. So we're differentiable now. However, let's have a look at that derivative. So if we write f primed of x is just, what is it, alpha x to the alpha minus 1 sine of x times by sine of 1 over x minus x to the alpha minus 2 cos of 1 over x, like so. Well, because alpha is already bigger than 1, because we've dealt with the case when alpha is less than 1, this term here isn't actually too much of an issue to deal with, because for small x, which is clearly where the issue is going to lie, actually this guy is going to just help us out, because when alpha is bigger than 1, well, the thing's going to work when x is small, right? Because it's going to control these oscillations. So this term is fine. However, this term is causing us a bit of a headache. When alpha is less than 2, right? When alpha is between 1 and 2, then we get something over x. And then, in that case, as x goes to 0, we can pretty clearly see that this is just adding fuel to the fire, right? This is just going to make the oscillations massive. This is going to absolutely explode. And so we're actually unbounded in this case. So when alpha is between... when alpha is between 1 and 2, where these are now strict inequalities, we're differentiable, but unbounded derivative. And hence also non-continuous, of course. And if we look at this again, but we've set alpha equal to 2, well then, okay, fine, we're not unbounded anymore, because this is going to be bounded by 1, plus minus 1, or whatever. And this guy gets bounded by this term here. However, this guy still is not converging to a limit. And so when alpha is equal to 2, okay, you're continuous and you have a bounded derivative, but you're still not, but your derivative is still not continuous. So there's more to the story. Alpha equals 2, we are differentiable, bounded derivative, but not continuous derivative. Right, so, and then eventually when alpha is bigger than 2, if you looked at that expression, then finally all the terms behave and we're just differentiable with a continuous derivative. But yeah, so we have in one family of functions, we can refute. Firstly, the guy who says non-continuous functions are not integrable. Immediately, we just pull out the topologist sine curve and we're done. You've been refuted, mate. All right, cool. Number 2, okay, you can be continuous, but if you're continuous, you better be differentiable. Well, again, just look at our function in the case when alpha is between 0 and 1, but not 0. Again, you've been refuted, mate. It's over for you. Your career is done. But then the guy comes back and he says, well, okay, fine. But if you're differentiable, you have to have a bounded derivative. You can't be differentiable and have an unbounded derivative, and that would just be lunacy. And in that case, we say, listen, just plug in alpha between 1 and 2. Career done again. He's finished. But then eventually he says, fine, fine. I bet you can't refute this though. You can be differentiable and have a bounded derivative. And in that case, your derivative must be continuous. I mean, it just has to be continuous. And again, you get refuted. Just plug in alpha equals 2. And boom, the derivative is not even continuous, mate. So, I mean, anyone who tries to say anything contrary to these statements, just pull out this function and their career's over. Thank you guys for watching, and make sure to check out, I might not have time this evening, but definitely by tomorrow, my full video on analysis counterexamples. I'm going to be ending everyone's career. Anyone who says anything, any analysis heresies, career done. Watch out for that video. And I'll see you guys hopefully in the study stream tomorrow. Ta.